by how evolution has probably come up with a much more elegant solution than I ever could. So to trans-aldolase, notice now we're breaking it in a 1,3 fashion. So this is a retro-aldol reaction. So you'll notice the bond we're breaking isn't between the carbonyl carbon and the adjacent carbon. It's between the alpha and the beta. So this is just a retro-aldol reaction, leaving us with the enolate and kicking out the erythrose 4-phosphate. So notice the first step forms this product here in red, and then the erythrose 4-phosphate. Okay, so those are the two products of the first step of the retro-aldol reaction. And then in the next step, it's pretty simple. Now it's just an aldol reaction. So we take our enolate, attacks the aldehyde. Aldehyde, of course, is going to become protonated. And this is the aldol reaction forming fructose 6-phosphate. Now you'll notice, though, it actually goes through the same type of aldol reaction that we learned about in glycolysis. What do you know? Okay, so these same mechanisms start to appear over and over. With the trans-aldolase, it goes through the class 1 aldol reaction, right, where it forms a protonated shift-base intermediate. So we don't use it as the ketone directly. Instead, we form the aminium ion, just like you learned about in the aldolase reaction. So just as in the aldolase reaction in glycolysis, the lysis portion was a retroaldol. It's the same reaction being catalyzed right here. It's just a different substrate. So retroaldol, starting with the aminium, and then it doesn't, instead of just then leaving you with the fragments, it's shifting, right? We're then doing an addition to an aldehyde to then form a fructose 6-phosphate. You're not responsible for this, but you are responsible for the trans-ketolase, okay? This is what you're responsible for. All right, so one last thing to talk